Okay. Grab the biggest sliver of chalk I can find. Okay, welcome back, everybody. So we're going to move on to trajectory optimization today. And I continue to enjoy your feedback. And people have been repeatedly saying they appreciate the high-level overviews of where things are going. Some people also said class is bussin', which is cool. I had to figure out what that meant, but I was my daughter was very happy that that was said, so thank you for that. I guess I don't watch enough TikTok, but yeah. So if things are not bussin', tell me, and we'll try to accommodate. So let me start from a high level and tell you what the big change is that's going to take us in from the types of stuff we were doing last time to this new formulation, which is trajectory optimization. Okay, so we've talked about a few broad strokes approaches, right? We've talked about dynamic programming in its full glory. You know, that's sort of the overarching theme of optimal control, and how do we solve optimal control with additive cost functions in particular. And we specifically dug in and did some work with value iteration, which, if you discretize, is just awesome. You can solve relatively small problems, but with arbitrarily hard dynamics, very interesting cost functions, and you can solve them very nicely if you're able to mesh the state space. If the state space gets too large in terms of dimension, then making a mesh that covers the state space becomes very, very hard, right? So the value iteration mesh-based approaches slowly die out in that way. The neural approaches will get you farther, but with less guarantees, right? So you got to play with that on the P set. There were a few special cases like LQR where we could go to arbitrarily high dimensions, but that required a linearization of the dynamics, right? The way that we could take our computational methods, maybe our reliable with guarantees computational methods, and make them go a bit farther was with relaxing the Hamilton-Jacobi to Lyapunov type approaches. And we brought in tools like sums of squares. People said, can you help us understand, why Russ is picking the things that he's picking to talk about, and why did I spend so much time talking about sums of squares, for instance, right? I really feel that one of the themes of the class that I hope is very clear is that we should be doing optimization to solve some of these problems, but the dynamics should matter, right? We're not, optimizing a humanoid robot should not be the same problem, probably, because we know more about it than like playing Atari or solving Go. There's structure in the equations that we should know how to exploit, and we should be able to make our optimizations scale and require less compute and be more reliable, right? And I spent time on sums of squares and through the lens of convex optimization, because that's a way that I know how to express to you the equations of motion showing up in the optimization in I think, deep ways. And I think there's even more good work to be done there, okay? They still, these will scale, value iteration on a mesh hasn't really changed in 20 years. You get, maybe went from 5 dimensions to 6 dimensions or something like that, but it's still exponentially bad. And if you have a state more than 5 or 6 state variables, you don't get very far with meshing. The sums of squares can take you up into tens of dimensions and do pretty nice things depending on the degrees of your polynomial. For Lyapunov alone, we can do, we did the humanoid, for instance. But they're still trying to solve an extremely hard problem, which is, and I emphasized it with the sums of squares, all of these methods so far are trying to solve the problem, let's say, for all x. Some of them sample, some of them do it on a mesh, but really fundamentally we're trying to find U is some policy of x, where x is the entire state space. Okay? And that's potentially a very, very hard problem. Maybe artificially hard problem, right? So if I think about myself as a articulated, rigid body, kind of flabby system, yeah? Right, I've got some number of degrees of freedom. It's not small. It's far bigger than I go with some of these, right? My state space is enormous, like impractically enormous. Like I don't have time in my lifetime to visit all of the states that I have in my state space, right? So I probably don't need a controller that works for every single state in my state space, right? I mean, there's some states I used to be able to get into that I can't quite get into anymore, I know, and it's like getting worse every year, but still, it's just a time thing, right? I just don't, there's the dimensionality of the state space is so large that I shouldn't have to try to understand. I need to think instead about solving for the relevant states. There's a couple states that I use when I'm walking, for instance, that are pretty darn important, and I should get those right. And there's some states that are completely ridiculous that I don't visit on a good day, right? And I shouldn't really worry about having a policy there. If we're asking to solve for all x blindly, then we're asking maybe too hard of a question. So this is, trajectory optimization is a direct attack at that. Instead of saying for all x, we're going to switch the language today, solve a smaller problem. We're just going to try to find some controller that works for a particular x0 for one initial condition, the opposite extreme. If you tell me what initial condition I'm in right now, I'll try to find a particular trajectory, so just one trajectory, not a function over the entire space, one trajectory that says what my control action should be for the next finite amount of time. Okay, and this is the way that we can blow up into very high dimensional problems, is by solving a more narrow problem, which scales only with the parameterization in time, not having to cover all of the states. I hope I'll make that clear in a couple different ways. This is the stuff that they use. I switched my picture to the newer Atlas picture because that's, and I'll have a video of Scott showing them doing trajectory optimization on this, if we get to it at the end. If not, I'll do it next time. Okay, so this is really stuff that does scale and is in practice a big part of what Boston Dynamics uses when they're making the humanoid do its tricks. I also thought, even independent of your feedback, I thought, you guys have put up with a lot of board work for a couple lectures, so I thought I would start with sort of an application, a case study of this stuff. That's one of the older fun ones, but it's still, I think it tells the story well of what we can do. So let me start by telling you, the story of how we made those airplanes land on a perch, and I'll give you a few of the details and work through it. Hopefully it'll motivate the math we do after. So it was actually, so I did walking robots for my thesis, right? And then it was when I was on the faculty market. I was going around and I was meeting all these interesting people. It's a great time. You meet really interesting people. A few people, they give you their complete attention for an hour. It's like a fantastic time. And I remember somebody said, so why are you working on walking robots? Why not flying like a bird, right? I was like, oh my gosh, that's the next thing I'm going to do. I'm totally going to work on flying like a bird. So we went, and as a junior faculty, I started trying to build robotic birds. And if you come into our lab now, this thing was still hanging from the ceiling on a wire. This is a 2-meter wingspan autonomous ornithopter. It's one of the first that could fly around. It had a breakaway beak, but it broke away before we took that picture. So you don't get to see what it looked like with a beak, unfortunately. But pretty cool, and it got me thinking a lot. Again, I was thinking this is a case where model-based control wouldn't work, and this was sort of my RL workflow of how to, these are really complicated dynamics here. And it got me thinking a lot about what birds are good at and what planes are good at. And one of the things that birds are good at that planes aren't very good at is landing on a perch. Okay, so if you look carefully at what's happening when a bird is landing on a perch, airplanes tend to keep at a pretty low angle of attack, right? This is the And there's a reason for that. It's because if you take your airfoil, right, and you increase the angle of attack, the airflow changes the way it goes around the wing. And at some point, there's a stall angle where if your angle of attack is too large compared to the oncoming flow, then basically the air can't wrap around the wing fast enough and it starts separating from the wing. And this picture makes it look pretty, but it's actually a pretty complicated thing that happens, right? So you can have a dramatic change in the lift and drag profiles of your system at this moment of stall, okay? And so it's pretty exceptional when you look at a bird landing on a perch to see them going like this, right? And if you look at the smoke trails, which you can just barely see in this picture behind it, then these birds are routinely going into deep stall, which is the thing that airplanes have tried to avoid, right? So we started asking the question, well, what if, could we make airplanes land on a perch like a bird, right? And we did actually do, I forgot to include the video of the flapping version at the end, but I'll show that at some point. But so we asked, is there a fundamental reason? Is there something about the kinematics of the wing or something really beautiful about the design? There certainly is, but could an airplane land on a perch? Is it a controls problem or is it a hardware problem? And so we just said, what's the simplest possible system that could help us answer that question? And we started building very, very simple airplanes and asked, can you make them land on a perch? Okay, so the first game is always trying to decide, define your problem. What does it mean to be successful compared to planes today and compared to birds today? And so I like to think about the dynamics in a robust way, and you've got airplanes that are massive with huge wingspans, and you've got little birds, and you want to somehow compare them on a fair scale. So the way you do that is you have to think about the dimensionless numbers involved, the dimensional analysis. So you can find parameters that are not dependent directly on the wingspan, but should compare across scales. So if we had a bird or a plane with mass m, wing area s, in a fluid of density rho, going over some distance x to slow from an initial velocity to a final velocity, the number of interest, the scalar of interest that we picked was a distanced averaged drag coefficient. Basically, how fast scaled, how much force scaled in a coefficient sense, are we, how effectively are we stopping? And it's really interesting to start going through all the data and starting to plot this number for different systems, right? So like a standard Boeing 747 landing on a runway at Logan, for instance, gets about a drag coefficient, an average drag coefficient over its landing of about 0.16. These were very approximate numbers, but we did our best. And then there's like fighter jets that are doing stunts that are sitting on their tail, on their thrust vectoring and trying to do like incredible things. One of them is this X-31, which is famous for a super short runway landing. Okay, it actually thrust vectors in order to come in like this. And it gets about a 0.3, right? Back in the day, there was a Cornell perching plane concept, which they basically would try to rotate up the body to get a lot of drag on the body, but keep their wings in the attached flow, right? That was the idea, was keep your wing, your control surfaces on your wings. So let's keep the air flow reasonable on there, but we'll set the body sticking up and then we'll stick the tail out of the wake of the body. So our control surfaces still have control authority, but we stop hard. And they were getting, based on just the wind tunnel numbers, they're getting about a 0.25, okay? And then there's some just awesome people at Harvard, at the Harvard Field Station. Andy Buehner is one of my favorite collaborators, okay? They study real animals, right? So I was like, okay, what can like a goshawk do? Or like, or some bird of prey. Or he's like, I've got data on pigeons. Do you want the data on the pigeons? So, but he also convinced me actually that pigeons are like really good. They're the dwellers of the city that have to like swoop in and get your food and then get out of there. That actually maybe they're as good as a goshawk. I still wanted the goshawk number, but in fact, when we were doing this, Will.i.am came through the lab randomly, and we like presented this stuff to him, and he had some hilarious line. He's like, "Oh yeah, pigeons have got mad stop," So. Yeah, anyway, so the pigeon gets a drag coefficient of like 10, Okay, like that's ridiculous. If I asked my Boeing 747 to get a drag coefficient of 10, its wings would just pop right off, right? This is like a structural thing that somehow defeats my dimensional analysis, but it's spectacular, right? Now a parachute would do that too. So the number alone is actually not quite enough. The fact that they stop fast is not what's surprising. What's amazing is that they stop that fast, like parachute-style drag, while still staying enough control to like nail a perch. That's what's awesome, right? Like bullets go fast, but they don't like land on a perch. Right? So tried to boil it down to its absolute essentials, right? So we built a simple glider. There it is. A simple glider, the simplest one we had. I actually, as I was going through my old videos, I found all these outtake videos of us crashing planes in ridiculous ways. But we finally boiled it down to these very simple ones, which were easy to fix if you broke them. We took the propeller off in the end. You don't actually need a propeller to stop, right? So we took the propeller off and kept the math even simpler. The wings are bent up. That's dihedral. Right? A few aero people are nodding. Yeah, that's dihedral, right? So that gives us passive stability in roll, basically. So we didn't have to worry about it just like this. It was just passively stable by basically putting the center of mass below the center of pressure. So it just gave it kind of a pendulum stability that kept it from veering off. So that's a good trick. The only control surface is the elevator. So it's one actuator. I'll show you the model. It had a total of 7 degrees of freedom in the end. And one actuator that was controlled with off-board sensing, and this was one of the early days of motion capture. Okay, so we also built these pretty ridiculous catapults. Okay, we like had enormous this like 80-20 sled where we would bring it back with a very stiff rubber band roughly, and we fire this thing off over and over and over again, and generated a bunch of data. And I thought it was going to be extremely hard to model. It's nonlinear, post-stall aerodynamics. But the data came out so beautiful and good. This was actually motion capture data differentiated twice. So to get forces out of motion capture data differentiated twice was pretty good. And for those of you that know your lift and drag coefficients, so the red is flat plate theory. The blue is the actual data. It's also pretty funny. You don't normally see data like up to 140 degrees angle of attack, right? Because that was like our plane, going upside down, but it's still stuck to the curve, right? So that's pretty awesome. Now the drag coefficient looks much more noisy, but this is actually not noise. If you look closely at it, and we built an entire experiment to convince ourselves, this is actually vortex shedding. So any one trajectory of this is actually a beautiful periodic motion in this data, okay? And in time, we saw these beautiful periodic motions, and we built a wind tunnel, an experiment where we could do flow visualization just to make sure we had it right. So we actually, down in the basement of Stata, we built this whole experiment up that took beautiful pictures. We would put titanium tetrachloride on the leading edge of the wing. It starts smoking like crazy. It's like, don't breathe it. Don't put your tools near it. It'll oxidize them overnight. And you'd fire this off, and that would just make this beautiful white smoke coming off the leading edge. And then you put a laser, you do a collimated laser so that it's illuminating just a 2D plane, and you take these pictures from the side, right? We worked really hard to get this like a few pictures. Now that looks like a pretty good experiment, right? I think. You can see we tried to get the seam of the glass out, but we didn't get that. It's pretty funny though if you realize we built it in the basement. Like it was in there, right? That we took all these pictures. That's like where the exhaust vent goes out, and it was low. It was very homemade, let's say. But we did understand the physics from it. Okay. From that, we ended up with this dynamic model with planar dynamics, thanks to the dihedral. Okay. The aerodynamics came from the curve fits, but they were simple curves in the end because it fit the data so well. The state variables now were the x, y, theta of the center, roughly the center of mass or center of pressure. One more angle for the elevator, the current state of the elevator, and then x dot, y dot, theta dot. But the way you control your control surfaces is typically not with torque. We had a little hobby servo, so we thought of it as velocity control, not torque control. which sucks because it's not control affine. That's one of this is one of the places in my travels that I've seen where it's not control affine really. The aerodynamics screw that up. The servo screwed it up, but it was because of the aerodynamics that we took that approach. Okay, so 7 degrees of freedom. Like at the time, I just don't think we could. I know, I mean, we tried hard to like do value iteration type approaches, clever function approximation, whatever. We couldn't. We have one control actuator, which means you have very little control authority. I can show you the plots of the control authority is very limited. So to be able to stick a perch, we needed numerical accuracy that we just weren't capable of getting with any approach to value iteration at the time. It broke the stack, right? We couldn't do sums of squares directly on the whole problem. What we ended up being able to do very successfully was trajectory optimization, okay? So this was the sweet spot where the dynamics were simple. We could do very effective trajectory optimization, and I've recreated the model and stuff in a notebook so you can play with it if you want. But we're going to do trajectory optimization on this. In fact, let me remember to wake it up so that I can show you in a few minutes. Okay, long story short, we built a model, we did trajectory optimization, and you saw it in the first lecture, but, oh no, you didn't because I screwed up the audio visual, right? But we can now land on a perch like a bird. The perch was a thing of twine we put across the lab, right, with some motion capture markers. Right off the screen here was a guy with a catapult, often me or Joe or Rick at the time. We would fire this thing. It would be more than 6 meters per second, 7, 8 meters per second sometimes coming into the motion capture arena. The perch was 3.5 meters away. The entire trajectory was less than a second, about 0.8 seconds was an average thing. So that dynamically, you could not have stopped that fast without having deep stall, without having a drag coefficient that was significantly beyond what you could get in a normal aerodynamic regime. All right. So I coded up the old glider model so we could play with it. I'll open up Meshcat here. I broke Apple Silicon this morning, so that was my bad. So I'm running on Deep Note here. And what's happening is from this initial condition, so we picked a nominal initial condition representative of what we were doing coming off the catapult, okay? And from that one initial condition, we're just searching over a parameterized trajectory with some conditions saying I'd like to be at the perch at the end, and I have some acceptable velocities at the perch, right? Some range of initial targets, of final targets, okay? It does its little optimization, it runs, and you can play that back, right? We can scrub through it, but it's a pretty dynamic regime. The elevator goes, yay, we go up into a, this is actually not as dynamic as I've seen. If you change the initial if you change the initial conditions around, you can actually get it to do pretty, come down pretty steep and all kinds of crazy things to try to bleed velocity out of that aerodynamic surface. Okay, but that ability to optimize directly over the trajectories, that's what we're going to do today. Okay, and what's going to work even for humanoids and the like. Now, since I spent some time on sums of squares, let me, show you ahead of, fast forward a little bit. Oh, first of all, how well did we do? Right, so the pigeon does have mad stop. We didn't compete with the pigeon. We did better than a MiG. I was pretty happy about that. We came in about 1.1, At some point, you actually need to flap your wings. And we did have I should have put the video in. We did have a version of a flapping plane. It was pretty ridiculous, but it did slow down pretty fast. Okay, so we were somewhere in the middle of this. Now here's the piece of the story that will take 2 lectures to get to, but we didn't just do trajectory optimization. Trajectory optimization is from an initial condition, and that solved, given the initial condition, what path do I want to take, okay? But the next time I launch it, I'm going to be at a slightly different, we never ran the same experiment twice, right? We're shooting it with a rubber band, right? It was like pretty approximate. So what we needed to do was figure out how to not only take that trajectory that was pre-computed, but stabilize the trajectory, which we'll see we can do with a local LQR or other approaches, okay? And then we actually computed Lyapunov functions around the trajectory to certify that if I was in some range of initial conditions, I would end up in some range of final conditions that would get me to the perch. And then it'll take more tools still, but we actually would then compose many of these. We would slowly fill the space with lots of funnels so that no matter when how we threw it off the initial perch, it would always land on we got to the point where Joe would just chuck it and it would always land on the perch. And that's a pretty, hard control problem in the sense that it was really on the edge of what the control system was capable of, but it became very reliable and very robust. Yeah, so does that make sense? Any questions about that? Yes?
Why didn't some of those guys work?
It's possible today we could make it work. I think we've just been learning more about it as, I think we were early in the days of sums of squares when we did those experiments. I would try it again. 7 dimensions is approachable, right? And we know more about how to write the trigonometrics and whatever. I think sums of squares has not yet been demonstrated at the scale of a humanoid for the types of maneuvers that you see Boston Dynamics do. So there's no doubt trajectory optimization will go farther. This problem is borderline. Yeah?
Can you use sums of squares in the Lyapunov control to control unit trajectory?
That is what we do. That is exactly what we did. So the question was, could we do sums of squares in the Lyapunov control to stabilize the trajectory? So you could, it's exactly what we talked about last time. So you can do the linear controller, and it will have some region of attraction, or you can try to do better by searching for richer controllers that think more about the nonlinear dynamics. Even the linear controller can do fairly well on this, usefully well. Like it becomes a practical controller. Other questions about that? It's pretty fun. We broke a lot of planes back in the day. There was a great video of us going, this big old plane, one of our early planes, and it just goes, we threw it, like you could just tell the guy, Rick, who was throwing it, was like so excited. He's like, I just spent like 14 hours building this plane. This is going to be awesome. And it went wham, like it didn't go like 3 feet before it. And then you could almost see in the video of it, like the shock wave going through the airplane and through Rick as he realized he had just broken his 14-hour build. So you should always keep the video running when you're working with robots. Okay, so let's get into it. Let's figure out how we did this stuff. So, the basic setup here is our standard optimal control formulation. We're still going to we're going to try to minimize a long-term cost. This time we're going to choose a finite horizon. We could say T0 if you want more generally, but 0 is fine for me. Okay, of L of xu dt. And where before we've been trying to say, let's sort of minimize over pi, let's say so we're trying to find some feedback controllers. This time we're going to be just minimizing over my u trajectory. That's how I'll write the trajectory from, that's u of t. I'm writing u dot is like u of t for u of t for t in t0 to t final. Just a shorthand for that whole thing, okay? Now, the cost function alone doesn't define it. We still need to say subject to my dynamics, of course, but also subject to some initial condition. We can relax that, but that's the basic formulation, and I think I like to emphasize that there because it really is, the difference is we're finding one solution through state space, versus all of the solutions through state space. And that's what allows us to scale and get, get bigger. We can also, in this framework, handle additional constraints. Torque limits, the elevator had velocity limits, strict velocity limits. That was a major limitation. You can say, don't run into things, right? Don't collide with the world. Each of them have different ways to write, but we'll talk through that. So it's not much different. The only difference that we've said before is that we've said let's do it for a particular initial condition, and instead of searching over feedback controllers, we're going to search over an open loop trajectory U of t. Okay. Now the way I've written it here, U of t is a function, right? It's a function of one variable. In order to start optimizing with it, I need to have a finite parameterization of that U of t, right? So I need to somehow need a finite parameterization. And a lot of the details come into your choices that you make for how do you parameterize your trajectories and how do you formulate the search. There's many different solution approaches to solving for that. Yes?
You say U is a trajectory. Is U like your input? Is this the same U?
Same U. Yep. This is what elevator velocity I'm commanding at time 3, for instance, or what torque am I applying to the pendulum or the acrobat at time 3. But I want to have a profile over time of the command input, of my torque input, let's say.
And then will the state space variables also follow a corresponding trajectory with this?
If I've satisfied this, so the question is, what about the state variables? If I've satisfied this part of the constraint, then we'll see formulations where you explicitly solve for x or you implicitly solve for x. Great question. Any other questions at this level? Yes?
So let's say you have like minor modeling errors in F. How would this work for a long time horizon?
Awesome. So the question is, okay, what if my F has got modeling errors, right? So this is where feedback comes to save the day. And you're right to point this out. So in particular, if I start solving far into the future and I have a limited hold on what, if I don't have accuracy here, what business do I have optimizing far into the future? Yeah, so we're going to start by closing our eyes and pretending our model's accurate, and then I promise we're going to follow up with how do you stabilize that, and a little bit of feedback goes a long way. It can make your assumptions valid, right? Or in the worst case, you can replan, and it's useful, even if the models are approximate. There are also robust formulations of these things. Okay, so I think we can start thinking very clearly about this. If we, again, go back and make sure we understand the linear case and then work back towards the nonlinear case. In the linear case, everything's beautiful. And in fact, it's even simpler to think about if we think about first the linear discrete time case. Okay, so let's think about how this would play out if we're working in a model where A and B are known with that kind of dynamics. Okay. So if I were to write down, effectively the equivalent thing here, right? So if I were to suddenly say, I want to minimize now the sum over some loss at a bunch of different times, subject to this constraint and subject to 0. Well, now I don't have to worry as much about this finite parameterization, because in discrete time, I really am just searching over, I have to find u0, u1, up to un. Maybe actually only n minus 1 might matter, but something like this, depending on how I've written it. Okay. But this is now a finite set of numbers I'm searching over, right? The number of control inputs times the number of time steps that I'm looking over. And I can minimize some objective subject to these, these constraints. Okay. So let's think about exactly what we would do here. How would I write that down? So if I were to use this as a constraint, then I could actually write a formulation where I said, let's make extra decision variables here for x also. And now I can really transcribe this directly. The name of the algorithm is direct transcription, so that was a play there. Okay. Okay. And this constraint here is now a nice constraint in the sense that it's directly on, each of these are decision variables, and this is linear constraint on the decision variables. Certainly, this is also a linear constraint on the decision variables, a bounding box constraint on the decision variables. Simple, right? If I were to pick this to be a convex function, for instance, our standard LQR objective, then actually we can write a convex optimization again with decision variables u and x and a bunch of linear constraints and a quadratic objective. That's pretty interesting. We did have a good solution for LQR for the full policy, but it wasn't through convex. There are ways to write it through convex optimization, but the Riccati equation, original parameterization, is not a convex optimization for all states, but for one state and finite time, it is a convex optimization. Okay? Because that objective is convex, and the constraints of the dynamics are convex. What's interesting is you can also, again, one of the great things about having the optimization-based formulation is I can add additional constraints. For instance, like, for all n, u of n is less than 1, for instance. I could put torque limits on. I could even put any constraints on x, too. Remember the cart pole, we did have constraints on x because we didn't want to go off the rails of the cart pole. You might have constraints saying, I don't want to run into objects, so there might be constraints on x. There's a surprising number of constraints you can write that are actually convex constraints on u and x that are pretty useful. In general, in the notes, I actually sort of call out, like, if you haven't thought a lot about convex optimization, I remember when I was learning it, I was often surprised by the number of things that you can, with some clever formulation, stick into convex optimization. There's often ways with slack variables or something like this to get the job done for constraints. Even some constraints that are geometrically non-convex, if you put them in a higher dimensional space, they can become convex. There's all kinds of clever tricks. Okay. So let's compare this then to the LQR we had before. What are the differences, right? One difference is we have a narrow solution, right? We only have a solution for a particular initial condition. but we have a reliable solver if we have this convex optimization. It'll scale to very large problems, by the way. Okay. The big new thing we've gained is that we can directly handle constraints. And in fact, if you were to go to anybody who's considers themselves a control theorist and say, what's the right solution for constrained LQR? They would say, you would write it like this. This is like the accepted way the right way to do constrained LQR. Okay, there are a few people that would give you other ways. You can try to, yeah, but 99% of control theorists would tell you this. Okay. And the reason for that, actually, and partly to David's question, is that even though this is only for an initial condition, these solves are so reliable and so fast that you can solve these on the fly, even for very large scale problems. And people have done that for years. It started off in the chemical industry, where chemical plants needed to be regulated, but they were pretty slow and computers could keep up. And now we can do it for Atlas and stuff like this. Not a big deal to solve those things on the fly. Even when n can be large and the state variables are large, if the dynamics are linear, convex solvers will scale for this pretty well. Questions on that? Go to the thumbs. Okay. Yes?
So, mathematically speaking, is the difference between this and the previous control? Is it like the fact that we're just explicitly solving for a specific initialization for a certain number of time horizon?
Not just time horizon. So the question is, what can we clarify again the difference between the original LQR versus this LQR? Is that, yeah? So I mean, the original LQR was finding u equals negative kx, where this was a valid controller for all x. Now I'm finding u as 0, u1, assuming x0 equals x0, right? So in fact, the few people that would maybe say, would not answer this as the initial thing, there are ways to try to write the policy. You can explicitly compute the policy for this, for these problems, but it scales badly. And it turns out we know that the optimal policy for this is actually a piecewise linear function with the potentially exponential number of pieces in the number of these constraints. Okay, and the value function is actually a piecewise quadratic value function. And there are people that try to compute that, but it blows up very, very quickly. Even for double integrators and stuff, it's pretty impressively hard. Good. Okay, so now if you're paying attention to when I said this, I mean, you might have thought, well, I shouldn't have to write x down as a decision variable. That seems pretty wasteful, right? Like I know how to integrate or multiply my differential equations here. It seems pretty wasteful to have decision variables for both u and x. Certainly, if I've solved for u, I can compute x by just simulating. So let's think about that. So what's the difference? We can write min over just u of, let's say, the same thing. Oops. As I write, so I've written LQR objectives so much that I got sloppy, but it's only convex if the cost function is positive, right? So forgive me for not writing that every time, but I can actually solve, right? So if I know u0, and if I have those dynamics, so if I have x0, x1 is just a x0 plus b, whatever my u0 is, right? X2 is what? A squared x0 plus a x1, which is this thing here, plus b u0. So I get these a to the powers. Okay, but I can solve all that out. And in fact, x of k is just, it's a function with some powers here, right, of function of u0, u1, u2, all the way up, okay? It's a linear function of u. I should just write it down. I know it, but I do want to get the signs wrong. Okay, so you actually can write a more clever thing here, where you can write down, it seems more clever, but we'll talk about whether it's good or bad. You can write down this entire problem using only u's by basically pre-solving away x as a function of u. It's a linear function, so I can substitute this in every time x appeared in my original problem, drop my dynamics constraint. It's solved explicitly, and I have now, you know, a potentially an unconstrained optimization directly on u. If I can add constraints like for all n u of n is less than 1, but I have solved away this dynamics constraint. And I have less decision variables. So it seems like obviously good. And some people believe in this, like with their core. This would be the shooting. This would be direct shooting method, whereas these are called direct transcription, where you put the extra decision variables there. Okay, and people who do trajectory optimization for a living, I'd say you find like 50% of them believing more in direct shooting and 50% of them believing in direct transcription. So that tells you this is not everybody thinks this is obviously better. The reason for that is that this a to the k, you get numbers up to large powers here when you solve this out explicitly. So for instance, if you've heard in deep networks people having vanishing gradient problems or exploding gradient problems, you know, the numerics of solving for this as a function of u0, for instance, and I take my dynamics and I multiply it to the t power, those numerics can get bad. That's one problem that it has. And they're also imbalanced, right? There's this, there's all these strange names for it. People would call it tail wagging the dog, right? The problem is that the effect that u0 has on your cost is dramatically larger. It has more time to impact your cost than u at time n, for instance, because it's multiplied by a much smaller number. So the scaling of that problem is potentially problematic for solvers. In the linear case, in the convex optimization case, the solvers are so good that you could do either of them and they're fine. There's really not a big difference. But when you get to the nonlinear versions of these, the solvers start having more problems and the differences become more acute. Okay, so this has less decision variables, but they're harder numerically to deal with. This sort of gets around, it doesn't, I mean, it still has the problem that initial u's can affect the outcome more, but it spreads out the numerical difficulties across lots of constraints. Right, so the solver gets to reason about all those constraints independently. Each of the constraints individually are numerically good, and so it's able to, I believe that this has typically better numerical properties. Also, when the dynamics get harder to evaluate, you can trivially parallelize that, whereas this one you really have to roll it out all the way. That was more, when you can roll out like 1,000 rollouts in parallel completely together on the GPU, that difference is less important than it used to be. But okay, but those are two fundamental different transcriptions. Okay, so I can make X a decision variable and add constraints to satisfy the dynamics, or I can solve away the dynamics by basically simulating forward and using only the control inputs as decision variables. Both of those carry on directly to the nonlinear case. Okay? Both of those have direct extensions into nonlinear optimization. Right, so if I have xn un as my constraint, that becomes a potentially non-linear, non-convex constraint. Or similarly, if I were to try to solve away x of n is the sum over my dynamics rolled out, it would be, or really it's the composition of like of f of f of f of f is what happens, right? This would be in the shooting approach. These are both non-convex constraints when you hand them to the solver. So how do people go about solving that, right? So how do you end up solving, if you tell the solver, you can write in mathematical program a function that you write it almost exactly the same way, but you just give it the dynamics that are nonlinear. The code looks the same, but the solver has to do dramatically different work, right? Once I have non-convex costs and constraints, then the picture you should have in your head is that I've gone from a problem that has decision variables u and a total cost, let's say j, that's some beautiful convex function that has a local minima, to potentially a much more complicated landscape that has the costs changing dramatically, or changing in complicated ways as I've changed my parameters u. So there's a bunch of different solution techniques that people use to do this. Okay, the ones that are probably there's a bunch. I'd say there's a lot of different possibilities. But the one I used in that example, how about that? Get my colored chalk. Is to do sequential convex optimization. In particular, since these are quadratics here, there's a sequential quadratic programming approach to solving these problems. And that's what's happening when, in mathematical program, it dispatches to the solver SNOPT, sparse nonlinear optimization. Okay, it's an SQP method. Lots of acronyms. Sorry. Okay, but the idea is very simple, is that we're good at solving quadratic programs, even constrained quadratic programs. If somebody gives me a nonlinear objective or nonlinear constraints, then a reasonable approach would be, given my current sample, make a local quadratic approximation of it, solve that to optimality, now get a new local quadratic approximation, wash, rinse, and repeat. And these methods can exhibit very fast convergence, potentially. They can get stuck in local minima, right? This one might well converge to this minima when it should have, I really would have loved it to converge to this. But these can exhibit very fast convergence to local minima for very hard nonlinear optimization problems. We have a handful of solvers wrapped in Drake. There's an IPOpt is another very popular one. That's an interior point method based solution. NLOpt we have in there too. A lot of different solution approaches to this. It's interesting actually now, nowadays, so Boyan and I were talking the other day that Nowadays, when people solve this problem, where F is a neural network, for instance, they tend to not use second-order optimization. They'll do basically genetic algorithms. So if you've heard of as CEM, the cross-entropy method, or MPPI, it's path integrals, multi-parametric path integrals. You know, these are also solving the problems, the same basic setup, but they're doing it by throwing out a bunch of particles because that's an efficient thing to do on the GPU. They'll throw out a bunch of particles and try to make an approximation based on those particles, and then update and make a new batch of particles, you know, roughly. But they're solving the same class of problems, these trajectory optimization problems. There's some important differences to using particles versus local gradients, which we'll cover more in detail. But those are in the same family of possible solutions to that problem. Okay, so is the basic setup clear? Yeah? Now, how do we do continuous time, right? If we do continuous time, we have to somehow address this. I need a finite parameterization of time. Okay, there's a couple different ways you could do it. The direct transcription way you could do it, let me go over to this board so I can leave that up. Would be you could just say I'm going to approximate xn plus 1 here as some numerical integration, you know, from time tn to time tn plus 1 of my dynamics, right? Plus I'm mixing continuous and discrete time here, but I hope that idea is clear. I can make the notation better if we need to. And in practice, we'll approximate that integral with some numerical integration. So sometimes you would just do xn plus 1 would be xn plus, let's say, my dt times f of xn. This would be the Euler integration, the Euler approximation of that integral. But you can also put in Runge-Kutta. You could put in any of your favorite numerical integration schemes here. I would recommend not putting in a variable step integrator there, because that messes with your solver. Okay, you'd like to have smooth behavior, consistent behavior as you change the parameters around. And if your solver's taking multiple steps every time it evaluates, different number of steps every time it evaluates the constraint, that can get to problems. Okay, but in general, we can make a discrete time approximation, use our direct transcription to implement that, and life is good. Did I say that well enough? I know I'm kind of I'm being a little sloppy with the notation, but yes.
Before in the second, not like the things that still up, the thing's been erased. You said one of the issues is like the a to the k. Looking at this, a is like the identity matrix, right here.
A would be the A is hiding in F here.
Oh, okay.
Right?
Never mind.
Yeah. Yeah. A is hiding in F. If I were to linearize that, then I'd have an A that comes from F. It would be I plus whatever I get from F. Yeah. Other questions? Okay, so this can work. This can work well, but it makes a particular choice. If I've written like this, or however I've written it here, this is making a particular choice about the way I've parameterized u. So if I were to plot like my continuous realization of over time of what I'm solving for u, the way I've written it at least, I've made a zero-order hold approximation of u, right? I've parameterized u with a finite number of steps. This might be u0, u1, u2, and so on, right? So that gives me some amount of control in my optimization, but it can lead to potential artifacts, right? If we saw that already actually in the way that when we solved the minimum time problem with the discrete time, we could lead to artifacts. It wouldn't actually get to the goal exactly, and it would move the decision boundary significantly because of these discretization artifacts. Okay, but if you're willing to go with that, let me warm up the solver here. If you're willing to go with that, then a few lines of code can solve our, almost all of the problems that we've run so far today, including the double integrator, for instance. So people did say that they don't get much out of seeing the code, so I will just show the results here. But this is, I'm going to just show the decision variables here. How about that? This is making new continuous variables for all of u and all of x. Okay, so this is my discrete, my direct transcription, and it can come up with these beautiful solutions to the double integrator. I hope you remember that one as remember these curves. I think my scaling is a little bit funny, so it looks funny. But remember the optimal solution to the double integrator is to get as fast as possible to some curve and then write it in. Okay, and it does this very well here, and you'll find that curve is actually up to the discretization. It can be arbitrarily accurate as you make the time steps smaller. I did something funny here. I solved for a minimum time problem, and if you look at the code, and even I wrote it up more carefully, there's a magic variable here of trying to pick the number of time steps so that the cost function gave me a minimum time. So I encourage you to look at and believe me if you think that was a total hack or not. But you can get minimum time type solutions by doing a line search in the total horizon. Okay, but there's another, there's I think a nicer way to think about parameterizing u, and that when you get this continuous time, I think the beautiful way to write this all up is with my favorite one is with direct collocation. This is natively continuous time. It doesn't even make sense in discrete time. Every few months, someone will ask on Stack Overflow, why doesn't Drake support direct collocation in discrete time yet? It's like, it will never support direct collocation in discrete time. It doesn't work. It doesn't compute. Okay, the way that you do direct collocation says, let's parameterize u as a function of t using a spline. So we'll do a piecewise, you can do a piecewise curve, okay? But we're going to use splines, which tend to be piecewise polynomial functions. Okay, so we'll define a finite set of segments, and in each segment we'll have a polynomial of some degree that describes the curve in that segment. Okay, it turns out for direct collocation, it's a direct method in the sense that it parameterizes both x and t as splines. And the sweet spot for this algorithm is to choose u of t to be a first order spline. And x of t to be a cubic spline. It's not strictly required, but it's kind of like, I don't know if anybody, how many people have thought about like Runge-Kutta 4-5. RK4-5 is like this magical integration scheme. Like why is 4 and 5 the one that everybody uses? Well, it's because the terms work out so that you can have a fourth order update and a fifth order update that share enough terms that it's particularly computationally effective. And the same sort of thing happens here is in the constraints that you end up writing down to make the u of t curves consistent with the x of t curves. It's magically effective when there's first order splines here and cubic splines down here. Okay? But the idea is more general than that. Okay. So the idea of direct collocation is you make your decision variables you actually write the discrete decision variables u of n, x0, xn at the breaks of the spline. Okay, so you're really parameterizing these numbers here, u0, u1, u2, for instance, x0, x1, x2, for instance. And by having x0, x1, and x2, we actually have, we have enough certainly, you know, if I have those two numbers, I certainly know that there's only a single first order polynomial that can go between those two. So having those two numbers completely specifies that curve. And it turns out that since I have the dynamics of x0 and x1, having the value of the endpoints of this cubic spline, and knowing that x dot equals f of xu, if I also have u0, okay, so I actually know the slope of those curves based on just the decision variables at the knot points. That completely specifies this curve with the 4 decision variables of u0, u1, x0, x1, and the derivative constraints. Up to a boundary condition, up to some boundary conditions. So there's one more degree of freedom writing around there. And we write that down by picking one more point on the spline. It happens for these cubic splines. The magic, easy to evaluate parameter is to evaluate the derivative at the midpoint, which is called the collocation point. Okay, someplace exactly in the middle of that spline. And you say that at this collocation point, the dynamics must satisfy and since x of t is fully parameterized by those splines of those derivatives, and u of t is fully specified, then you can write down one extra constraint here that says that the slope in the midpoint must satisfy the dynamics, and that fully specifies the entire curve. You do it for each segment, you add these collocation points. And that does a beautiful job of searching directly over the first order u's, cubic x's, working directly with the slopes of these lines. You can think of it as doing a type of numerical integration, but it's doing it very effectively because it actually gets third order accuracy with only a handful of evaluations. It's a particularly effective one. Yes?
Sorry, I didn't understand it. Can you explain again why you need the co-location point?
Yes. So the question is, why do I need the co-location point? So if I were giving you x0 and x1 and u0 and u1, then that would completely define the whole curve. You wouldn't need anything more. But x0, x1, u0, and u1s are decision variables. So in order to figure out what x0 and x1 should be relative to each other, you have to take away that extra degree of freedom by specifying the dynamics at the co-location point. Yeah. So it's interesting to think about it for a second here. So when I do integration like this, that's direct co-location, this is always doing integration forwards in time, right? These approaches are restricted to the class of numerical integration schemes that are causal. They march forward in time. The next step only depends on what's happened in the past. Intuitively, one of the reasons that this obtains higher order accuracy for less evaluations is because it's breaking that assumption of being causal in time, and it's solving for the entire curve simultaneously. It's just telling the optimization about all the pieces, providing integration constraints that are acausal, and allowing it to achieve better accuracy for less evaluations. Okay, so I want you to see some of the details and understand some of the nuances that go in there, but I also want you to know that this stuff is pretty well bottled up now, so you should appreciate why to call the different classes, but you can also just hammer on these classes and make them do pretty awesome stuff. So in Drake, there's just a direct transcription class. You hand it your system. You can add extra constraints. You call solve, and you can solve the same sort of optimization problems. This is the double integrator once again. Instead of me building up the problem by myself, I just called the direct transcription. It added all those constraints with a particular integration scheme for me. You can do more, right? So this one I chose to do direct collocation for the pendulum, which was natively continuous time. No more magic numbers here. 21 was arbitrary, not magically chosen. Okay, and I can ask, go ahead and solve the trajectory optimization problem for the pendulum. And in this particular case, I took a very large cost on input, and I put a bounding box constraint somewhere that was a very strict torque limit, basically. Torque limit here was 3. 3 is not stupid. I guess I just only turned the cost on the effort up. Okay, this is a piece of the eyeball of the pendulum. This is the upright condition. This is the initial condition, right? And it found a very long trajectory that found all those pumps. This is it going like this, right? All the way, it eventually got up. It's like doing all those pumps in order to get up, just like this, right? Just by solving the nonlinear direct collocation. You can see the resolution of actually the sampling is probably how I plotted more than the curve, but beautiful and robust solution for these small problems. And they swing up, there's no question that it gets to the top, because I put a constraint actually at the top. I guess I didn't have to wave my arm around. I forgot I made the simulation. Right. I actually put a constraint saying that the final solution is at the goal. Add a bounding box constraint saying the final state is directly at the desired final state. So the whole optimization was done subject to this constraint that it gets to the goal. Okay. All of the systems we've looked at so far are approached nicely with sort of this class of solutions. They all solve instantly and then render slowly, generating animation. Oh, here we go. Okay. Swinging up the acrobat. Whoop. Now this one is actually, do you remember I showed you, I actually showed a MATLAB version of it going wham, and just like super impressively going up. And this one's kind of wiggling around. I think SNOPT got worse. It means I wrote the optimization badly, I guess, but it is subject to local minima. But it like happened between SNOPT version, 8.3 and 9.1 or something like that. So that, I will say, as much as I want to applaud these approaches, they're frustrating to work with. They don't have guarantees. Someone can change the solver backend and your solution will change. If I change the initial condition a little bit, the solution can change. They can be very frustrating. But they can generate incredible demos. Okay. Cart pole, no problem. We can handle this one. The cart pole, I give a few different examples of different things. The Acrobat was handwritten dynamics. This is using the multi-body plant dynamics. Still solves instantly and then renders slowly, but we can swing up and balance these things. People use this stuff in autonomous driving, right? This is a standard planner for writing, for running an autonomous vehicle. Given current ideas about what are the obstacles around me, would be doing a small trajectory optimization. Oftentimes, they are similar to the sequential quadratic programming of this. A lot of people will think of them as solving this, but they will do linearizations of the dynamics and the constraints and solve these repeatedly on the fly, on the vehicle, in order to drive these things around and not run into people. And like I said, this is really the stuff that Scott talks about when he talks about, I'll turn the volume off, but this is when they talked about how they do parkour, right? They make libraries of these offline computed trajectory optimization, and they stabilize them on the fly. There's details in here about dealing with the contact, okay, that we'll cover when we talk about walking. But this stuff can go far. It's also, I have to say, so there's, I hope some people do projects on sums of squares. I hope people do projects on all kinds of different things. A lot of people over the years have done cool projects with trajectory optimization. So like for dynamic soaring of vehicles, I use that example of the Albatross sometimes, and Lucas went off and made an incredibly good trajectory optimization solution for dynamic soaring, where he put a basic aircraft vehicle in, computed trajectories, to basically do, this was even like a ridge soaring example, okay? And he had it working so well that he was able to start almost using it like a tool to understand how an airplane would perform in different environments and different situations. It became a reliable enough tool, and this was his final project for Underactuated a few years ago. So the basic recipe is pretty simple, I hope. The details are choices of the numerics of how you write these things in, and choices of the solver, which I'll go into more details about last time, but I hope I gave a high-level version of it this time that gets us started thinking about that. Any other big questions about today's version of it?
I have a question about that.
Yes.
So I'm wondering, if we have x0, x1, and xc,
Yes.
does that guarantee that the actual x in continuous time will follow the spline?
Great question. Okay, so the solution, so let me repeat the question. The question is, if I've parameterized x0, x1, and x2 as a spline and then written these constraints, on the co-location points, what can I say about the real solution? So the solution to like the pendulum is not perfectly described by a polynomial, piecewise polynomial over time, right? It has elliptic integrals and stuff like this inside it, right? So this is only a numerical approximation of the true solution trajectory. Just like you would say in Euler integration or Runge-Kutta integration or something, each approach has some order of accuracy, meaning at what rate, if I increase the number of points, will I increase the solution accuracy, okay? This one has a third order accuracy. It turns out that you can take quite large steps and have fairly small numerical errors in your approximation, but they will always be a numerical approximation. So what happens if you take, there's certainly cases where you can take the u and x that you get out of your perfect model, you simulate your u back with this certainly happens with perching, for instance. If I were to just simulate the open loop u back on my full simulation, I've not changed the model at all, my equations were exactly accurate, but I just numerically integrated them a little differently, I'll just miss the perch, okay? So the way you make that good is by stabilizing it at runtime. You should only think of this as an approximation that helps the solver find this and then find a way to stabilize it. Good?
When you say stabilize at runtime, what do you mean? Like, do you mean like take account of feedback?
So the question is, so we're gonna, the next lecture is trajectory stabilization.
Oh,
So I will have a satisfying answer, I hope, by the end. Okay, see you then. Yeah.